Okay, welcome back to the next session. Here we want to move, we completed the MRI physics module, and as per our template of coverage, after physics, we will do the data acquisition or the instrumentation and then move on to the image reconstruction and image quality. That's how we have been covering each of the modules at imaging modalities as well. So after completing the MR physics in the last module, we now proceed to the remaining part, which is going to be starting with the hardware part and then focusing on data acquisition, reconstruction and image quality. In fact, the object for this particular session of the video would be mostly on just the MR hardware and magnet perspective. Okay, so we'll start. I'm not going to do a review of MR physics as I have it here, because usually when I do in class, it is after a week, and so I have to refresh. But now that you have the video, maybe you should finish viewing the previous video again and then start with the new one. So that will save some time. Okay, so how does it go to the next slide? Okay. So let's skip the process involved in MRI, because this is supposed to be review. We have gone over this several times as to how we go about this, so you can refresh yourself before start of this material what we were doing until now. Okay, so where we will jump is, again, despite me showing it here and asking you to review previously, we start answering this question. Okay, we have already covered all the physics. Okay, what is it missing? How do we do this jump from, we are interested in MRI, we covered the physics part of it, we understood what the signal is, we understood the contrast mechanism. Now, how do we, in fact, we also pretended we saw several images as well, but we didn't really answer the question as to, all the development material we did was taking a small voxel and we were talking about the spin physics and how to manipulate the spin. But how did the different locations have different properties, right? How did we execute that? How do we realize that? That part we have not covered. So that is the question here. How do we do this? Because if you want to do this as an imaging, we need to measure at each location. Therefore, we should be able to tell, oh, this is the proton density here, density there, and therefore you get an image. How do we do that? Right? So before we go into the details, broad side, think about the first principles, what we covered. What we covered is, in nuclear magnetic resonance, NMR, the nuclear spin is the important guide. And we described that if we are biomedical, we are interested in hydrogen proton. So hydrogen proton had one gyromagnetic ratio. That is the Larmor frequency. If you were to spin, the Larmor frequency is unique, right, for hydrogen. And it was some 42.8 megahertz per Tesla. So you have signature Larmor frequency, and I want to see how the hydrogen or proton density is distributed in the body. So the logic would be straightforward, right? How do I change? Can I change the Larmor frequency? Well, the Larmor frequency for hydrogen is unique. However, it is a function of Tesla or the field strength. What happens if I change my field strength at different locations? What will happen? Oh, different locations will have different frequencies. So then I can, if I know how they distribute, if I manipulate the different magnetic field at different locations, then I also know where the frequency is coming from. I can say it is coming from that location, right? Very intuitive, very simple concept. Okay, so that is what we will do. We'll talk about using gradient coils, right, to encode your magnetic field at different locations in X, Y, Z, so that the Larmor frequency changes. So therefore, from the signal frequency, we know where it came from, right? Very at the bird's eye view, that is the concept. Then we'll talk about applying, right? That is first is the generation of your magnetic field, and then apply magnetic field and manipulate. So you have to have RF pulses that you can apply when you want. So finally, apply, you measure the signal, Again, we'll get to this when we get to the reconstruction. But this is the challenge in MRI. We are always worried about signal measuring in time domain. That itself is complicated. And then doing all the measurements, signal processing, the typical way we do. The beauty and also the challenge in understanding MRI comes, the data you are actually measuring, you are actually measuring sampling the frequency spectra. Right? It looks very difficult to understand if you, but imagine what you are doing. I'm saying you're changing the laminar frequency and you're measuring the signal. What was your signal? Free induction decay. So I'm just having, so I can take the power spectra of that will have the frequency that you're taking out, the laminar frequency. So I have the energy, remember the Parseval's theorem. So I have some signal, I have some energy for that particular frequency. So the energy at that particular frequency, when the frequency is changing at different locations, that means I am having the frequency spectral information at different locations. So I have the Fourier transform directly. I am measuring the Fourier transform directly. What I want is the object, not the Fourier transform of the object. So we should be able to reconstruct that. So what we are measuring turns out is nothing but you are measuring the energy in different frequency, which is nothing but your Fourier spectra, Fourier transform, right? So we'll get to that, but start to appreciate that. We go to instrumentation first. So how do we enable this? That is what is the first goal. So this is a block diagram version of the components, right? So you have a main magnet. You are expected to have gradient coils. What is gradient? Gradient means slope. That means there is a change coils. So you have a gradient coils in XYZ means you have to be able to change something in XYZ. What is that something? That something is your magnetic field. So you have a main magnet and you have the ability using gradient coils to change the magnetic field in different locations of XYZ. And then what do you need? You need to apply excitation and receive. So you have the RF coils, right? That is going to, the RF electronics will come in to enable the excitation. And then you have to have some computer so that you can code the sequence. Remember the controller sequence, the pulse sequence programming that we talked about. So you need some sequence computer. And then of course get the data, you have to do some image reconstruction and you have to have a big console that can control all of this. Okay. This is how a typical MRI, I'm sure you would have seen it. You have a bench, you go, that is the big board that you see. Patient goes in. A very important point that I would like for you to alert, until now we covered physics. I've been always saying floor to roof as your Z, because it is easy for me to do this. And the transverse was TXY was my floor. Here I'm going to make a switch because the patients are not standing, right? They are lying down in the bed and going in. So starting now, almost all reconstruction, all the analysis that we will do, we will relate this axis of the patient going in as the Z axis. Okay, and therefore the axis now is rotated. So now whatever I'm saying Z is not going to be here. Z is going to be the board inside the patient, along the patient's foot to head. It was foot to head before also, just that I was standing or I was sitting here. Therefore this was Z. Now the patient is lying and therefore Z axis is also lying. Okay, it is from foot to head. That is my Z axis. That's the only change. Otherwise, you look how complicated it is, right? So this is big, you need a special room. So the cost and complexity goes up. But let's go into the details. So the essential components that we are going to look into a little more detail is, you have to have a magnet. Why do you need a magnet? You need a magnet to polarize everything, align in a particular field direction. And what you need, it has to be strong, it has to be uniform, and it shouldn't change with the time, right? I'm supposed to have same magnetic field while I'm doing the experiments. If it changes unknowingly, randomly, then it will become difficult for me to encode where that frequency came from. So that is a generally superconducting electromagnet is used for that. We'll go into the details of different types of magnet in a while. Then you have to have gradient and shim coils. Gradient we already talked about, some sense you understand. You have to change the magnetic field. That means you have to create a gradient. So you need a coil and that will change. The shim coil is a new one. What is the shim coil? Shim is nothing but, see, we want homogeneous magnetic field, the V naught, right? And it should change only as per our design requirement. The gradient should be as per our requirement. So we know which frequency came from where. But magnet being magnet, I mean it's a material, it can have some inhomogeneity, fluctuations, right? You don't want that. So how do we smooth it? How do we make sure that the field is homogeneous? You need to have shim coil. The shim coil essentially tries to compensate for any inhomogeneity so that the magnetic field, it turns out to be homogeneous. And your gradient coil, likewise, you should be able to change the P, right, your magnetic field in linear fashion over X, Y and Z, the three orthogonal directions. Let's go into first magnet, and then the next video lecture we'll cover gradient and shim coils. So going to magnet, right? Of course, then the component that we'll cover is RF coil. You need the RF coil to both excite and then detect the transverse component, right? So there are several ways to do it. You could do it separately. You can have a transmit coil separate, receive coil separate. But typically, it's a hybrid. Most systems have a body coil that will be used, but on top of it, for getting higher signal to noise ratio, they also do a specific anatomy specific coil. If you go for scan on your elbow, you can have a coil here. You don't want to do the whole body, right? Whole body might be there. You might find a fracture in the knee. Then they'll put a surface coil on the knee to understand the knee even more better. So mostly it's a hybrid, but generally there is a body coil that comes inbuilt with the scanner system. So we'll look at this also when we get into the RF coils. So first is the magnet part. So magnet, what do we want? We want the static magnetic field. So what are the demands? We know the demands before we go in. One is it should be homogeneous. It shouldn't change. So two is it shouldn't change with the time, right? It has to be stable with the time. I buy a machine, I buy a magnetic field as a magnet today. That magnetic field strength should be same. Whatever is calibrated, whatever is listed. It's a 1.5 Tesla machine. It has to be 1.5 Tesla over a long period of time. It cannot be 1.5 Tesla only for the first month. Then you are in trouble. So demands are, you have to have spatially homogeneous field. Should be stable over field. It has to have a strong field. We will define what the strong field means, right? I mean, what is strong, what is weak is relative. But you need a strong field. You know that from before. Why do you need a stronger field? More the field, better the signal quality. Go recall the signal equation that we got. It was a function of magnetic field strength, right? So, want better quality signal, you have to have better field strength. And then, of course, patient access. The magnet should not be small. It should be big enough so a patient can go in and come. Okay. That means you have to keep all the spatial homogeneous field over a larger volume. So there are different types of magnets: permanent, resistive, superconducting. I'm sure you are familiar with permanent magnets, right? Several small scale you would have seen. All the, in the refrigerator we put souvenirs, right? They're small. It always has magnet. There is always a field strength to it. It is so small that it holds your souvenir in place, but otherwise it is already, it's permanent. It's always on. The magnetic field is always on here. But you see the strength is, we don't know much at this point of time, but we know it is right now in fractions of Tesla. Whether that is good or not, we will see. Then there is a resistive, where again the magnetic field strength that you see is also fraction. And then there are superconducting, which you see that it is from fractions to 3 in some cases in research. There are 9.4 Tesla. So now maybe if you have a general experience, you would have seen MRI scanners advertised. They have 1.5 Tesla as very common. There are 3 Tesla. So none of the permanent or resistive is in that range. So you can already understand most of the existing MRI scanners use superconducting magnet, and you get the Tesla or field strength in the range that is currently used. So why is it so permanent magnet? Even though I said what it is it's a special alloy. It has its good property. It loses very fraction of magnetism over time. Several of your magnets that you put in the refrigerator is is there for a long time. However, it is only less than 3% of all magnets that are used in this business. Why? Because although it has these advantages of low cost, you don't have to have any electrical system, right, to power it or power. It's always on in that sense, and low maintenance cost. And also the fringe field is very small. So these are all advantages. Despite that, it is not used very much because of these two major disadvantages. Okay, always on. So that is desirable, that is not undesirable. In case of a small field strength that you use in your fridge, it's not going to affect us. So it's okay, it can be always on. Whereas here, if you have a magnetic MRI machine and it is always on, then you have to be careful, right? Your safety, everything is going to have an issue with that. So it cannot have always on. And of course, it weighs over 15 tons. That means it's huge. You need a special infrastructure to even house it. Okay. Of course, the field strength, as we saw, is also very low. That is another major issue. So what about resistive magnets? Again, resistive magnets are slightly better than your permanent magnets with respect to its advantages, in the sense that you can turn it on and off. Okay, and it doesn't need you can turn it on and off, and you don't need to have any special cooling system. Of course, we didn't have cooling system even in the permanent magnet. Why is this an advantage here? Because the superconducting magnet that we are going to talk, you will need all special systems. Right? So in that sense, this is advantage because it doesn't need any dedicated cooling system. But again, here the disadvantage is this. The disadvantage is now you are running it out of electricity. So if you are running it out of electricity, if there is fluctuation in your power supply, which is very common, right? Then your current is going to change, and that current is going to change the magnetic field. You don't want your magnetic field strength to change. That is a first requirement. So this has a basic limitation, and also you saw that because of that reason, our Tesla was also in the fractions. Okay, so this is also not that advantageous to use. So comes the superconducting magnet. What is superconducting? It is kind of another resistive. Like what superconducting is also like resistive, but I'm sure you would have understood what superconducting means. So you have less resistance. So it's also resistant, but the resistance goes down with the temperature. So it's a different. You can think about it as a different version of resistive magnet, which has the advantages of the resistive magnet, but it overcomes some of the limitations, right? So essentially, you have a niobium titanium wire is a superconducting material. So if you are superconducting, you have to keep it at low temperature. Here, liquid helium is used essentially to cool this niobium titanium at less than 4 Kelvin. So from room temperature to this temperature, there is a real rapid jump. So in order to avoid that, you also have secondary coolant, which is liquid nitrogen, so which is at 77 Kelvin. So you have a gradient way. From the room temperature, you have liquid nitrogen, and then you have the superconducting material cooled by liquid helium, and then you have to have ion shield so that you don't let the stray fields affect it, and you have to have vacuum. So you already see that the sophistication of the setup has increased. Okay, but clearly this is having more advantages than the limitation, and therefore this is popularly used. Okay, so what does this do? You can think about it as a different way of resistive magnet. The major advantages here are superconducting. So the no electric resistance at low temperature, and therefore all the less current is needed. Your loss are less, right? And your active shielding. By putting an active shield, you can contain the field strength to a restricted location. And now maybe, weighs about 5 tons is listed as an advantage here. You might wonder 5 tons is still huge. No. Why is this an advantage? I think it is the relative context. We covered resistive magnets or permanent magnets before. What did we say? Permanent magnets? It was 15 tons. So this is advantages. This is lighter than that, but it has certain advantages. You can on and off when you want, but it has more advantage than resistive. There also you can on and off, but here you can on and off without much resistance, and you can do active shielding, and so you can drive up more field strength. Of course, it has its own disadvantages. Disadvantage mostly to do with the complexity and expensive. It is expensive to make, and therefore the price actually goes up with per Tesla. That is per. This is how they talk. If you go from 3 Tesla imaging 1.5 Tesla to 3 Tesla, your complexity of the infrastructure is going to go up, and therefore cost goes up. So if you are referred to go to a diagnostic center, if they have 1.5 Tesla, you'll be charged some amount. But if you go for a 3 Tesla, it will be more. You might think, oh, it's the same MRI scan of my knee, for example. But the cost is different because it's different Tesla. What do you gain? Higher the Tesla, probably your image quality is going to be better. Yeah, so that's the price that you end up paying for. Okay. And so large installation. This is generic disadvantage from the MRI modality. It is fantastic, but technically it is fantastic, but operationally it has these disadvantages of large infrastructure requirements. So what is typical specification that you get? You can get field strengths from half a Tesla to 9 Tesla. Most common is 1.5 Tesla. You also get it with the shimming. We already talked about shimming. What is shimming? Homogeneous field. You can maintain homogeneous field. So there are several techniques of shimming it: passive shimming, active shimming. So several machines that come out with superconducting magnet as a component, you get it better than plus or minus 5 parts per million, right? So this is the shimming that you get, and you can, of course, you get this magnet with also minimized fringe field. So these are specifications that are typically available with superconducting magnets, which is why it is popularly used. Clear?